Everybody got my email. Okay, good. All right. Okay, let's see. I'm going to wait another minute for Mr. Moore, for Mr. Williams. I'm sorry, Mr. Williams. So what did y'all do? Who traveled the farthest? How far did you go?
Kansas.
That's pretty far. Did you get caught up in the storm? No.
I think. When was the storm?
The big one was really right after Christmas. It was like 2 days after Christmas. There was, the tornado in Dallas and
No.
all that mess. The flooding in Missouri. Was there?
It rained when the first day we were there, and it was really wet, but I mean it wasn't like catastrophic flooding.
Can anybody?
At the same time, just somewhere else.
Can anybody beat Kansas? Oh, there was Virginia. That's probably Kansas is farther, right? Anybody beat Kansas? I went to San Antonio. That's pretty far. Okay, so I guess we'll start without Mr. Williams. So this is the second semester of the introductory physics, and we're using the textbook that I forgot to bring now. This is the E&M textbook, second volume of the Physics for Realists. And has everybody gotten a copy of the book, or is there still people? Somebody not yet gotten a copy? Okay, Mr. Rutherford. Okay. Do you have them on order? Okay. I think the library has a reserve copy, so you have to leave it. You have to read it here, but you can.
They still have a bunch of
Okay, in the bookstore. All right, good. They hate having copies left over there, so go buy. If you haven't ordered a copy, go buy it from the bookstore. So there is a little bit of assignments from the mechanics book, so keep your mechanics book handy, and you're going to refer back to it throughout the semester, because everything does build fundamentally on the mechanics, and we'll talk about that. Why it is the order here that we do mechanics first and then electricity and magnetism. There's a very sensible order to this, both historically and also logically, why it progresses in that way. So we're going to go back to the mechanics today. We're going to review. Today is review. And you'll have an assignment for Friday, which will start the E&M book. This classroom, I'm using this classroom because we're recording the lectures for the whole semester, just like I did mechanics. So there's a set of lectures from 2.5 years ago for the mechanics. It's online, and a lot of people are using them. The book does take some, to teach it, some understanding for the professors as well. And so there are a number of professors who are interested in learning about the book, and one way is just to see how you're using it in the class. And also I've had a number of students who are studying it, and the lectures are really helpful to go along with reading the book, because just reading the book is kind of a challenge, right? I mean, you can say that, you know that. It does help to have some explanation to go along with it. Okay, so we're going to start off, let's see, usual stuff, Blackboard. A lot of materials on Blackboard, so the assignments are on Blackboard, the syllabus, all that sort of stuff. Bathroom, by the way, is out here to the left. You go around, it's just through over there, so it's not bad. Okay, so let's begin. Then, do you have any logistical questions before we go into starting the review? Okay, and if you see Mr. Williams, straighten him out. He's gotten lost or something. He's still wandering around the library, maybe. Yeah, one other thing, I guess, Mr. Alt, do you know where the undergraduate lounge is?
Bottom Kiner?
Yeah, it's in the first floor of Kiner, down a couple of doors down from the office. So, and also, so please, and if you're forming study groups, study pairs, whatever, please remember to include Mr. All in that. He's got some catching up to do. And so please help him out. So let's. So this will be helpful for you also. This review. So okay. So what? Let's start. I'm not going to try writing because I don't have a good stylus, but don't really need to write this, I think. What is physics?
A rigorous study of the physical world.
Good. Rigorous study of physical things. How about physical world? Not bad, but more specifically, physical things. So what's a physical thing? Somebody besides Mr. Miller. Ms. Myers.
Something that is and can be something else.
Right. Something that is. It is something. A physical thing is something and can be something else. So it actually is potentially otherwise. That combination of those two things is characteristic of physical things. Okay, so what is, and that's what we will mean when you're going to read about matter and material in this book. That refers to the potency of something. So a physical thing is actually one way, potentially another way. This pencil is actually there, it's potentially over there. That potential to be relocated is referred to as material, the material aspect of something, matter. So matter is also a physical thing, and a material thing means the same. Those two words, material and physical and matter, all refer to the same aspect. Okay? So what is a body? Somebody else, somebody new. Yes, sir.
Is it a substance or a group of substances?
Not quite. Not quite. Bodies usually are substances, but that's not quite what's...
Something with extension.
Yeah. Physical things have extension, and physical substances have extension, but a body is a generic... I'm sorry?
An organized...
Not necessarily. No. You remember, Ms. Wheeler? You're saying no to that one, but do you remember?
It's just kind of a generic term for any.
That's it. It's a generic physical thing. Right. A body is a generic physical thing. So we refer to it, but generically it could be either a single substance or a group of substances, and even sometimes by extension a part of a substance we can refer to it, thinking of focusing on that. So a body is a generic physical thing. Okay. So what is abstraction then? Now let's hold on to that one. We'll come back to that. I'm going to follow my notes. What are the first principles of physics? We have physics as a study of physical things. What are the first principles of physics? There are 5 of them. I won't. How about we do one at a time? Each person do one. Mr. Sutton, what's the first one?
Things exist.
Things exist. That's really primitive, right? We're really talking about basic stuff here. Go ahead.
Things change.
Things change. Good.
Principle of non-contradiction.
Okay, the principle of non-contradiction. Can you say the principle of non-contradiction for us? By the way, this room is mic'd. You're being recorded, not your faces, unless you stand up. But it is helpful for people listening to the recordings to hear your questions. So try to speak up a little bit so the mics can pick up your questions and your answers.
Something cannot be and not be the same way at the same time.
Good. That's the backwards speak, or the negative way of saying it, which is the common way of saying it. The positive way of saying it is that something is what it is, which sounds like you're not saying very much. But what it means is that existence and non-existence are mutually exclusive. That non-existence is the absence of existence, and that you can't have something that is and not is at the same time. Okay? What's the last one?
Principle of causality.
I'm sorry, I'm on number 4, aren't I? Yeah, principle of causality. Can you say the principle of causality, please?
Something cannot change itself.
Something cannot change itself, right? And the wording is very precise there. Something cannot change itself. The itself and the something have to be precisely the same there in order for the principle of causality to make sense. Okay, and the last one is a little bit longer.
Everything is either a substance or a part of a substance.
Not part of a
Extension.
substance. Property of a substance, right? Yeah. So, physical thing exists either as a substance or as a property of a substance. So, what is a substance?
Something.
Go ahead.
Something that exists of itself.
Substance exists of itself, and a property exists of a substance. Good. Okay, so how do these first principles differ from mathematical axioms? These are not mathematical axioms, and what would be the difference? Somebody hasn't had a turn yet. Yeah.
They're based in the real world and on real things.
That's
not
right.
Like ideas in your mind.
Good. Yeah. So I'll take part of that answer. Certainly, the physical principles come from nature, and we observe them, and they're expressions and having reflected on what we've understood of the world around us, they're expressions of our understanding of the world around us. Now, ideas, okay, now we haven't spent much time talking about ideas exactly. We talked about abstractions. Ideas come from the physical world. All of our ideas ultimately come from the physical world, but we can play with them in ways that don't necessarily exist in the physical world. So I can conceive of things in my mind that don't exist as such in the physical world. So what is the difference then? We talk about two different things. There's the being of reason and the real being. So what is a being of reason?
It exists only in the mind.
Exists only in the mind. Never exists outside the mind. That's a being of reason. A real being exists outside the mind. Not always, but can, right? But a real being would be something that does exist outside the mind. The mind can conceive of things separately. So now we're talking about, well, we'll get there. Okay, I keep wanting to jump to that. I'm going to slow down here. Okay. Okay, now it is time. Abstraction. What is abstraction? It's the power of the mind. Yes, sir.
Isn't it to consider certain properties without considering all of them?
Yes, that's right. To leave out, to focus on some aspect of something, leaving out some other aspects. So can you give me an example of abstraction? Math is an abstraction. Yeah, that's right. The concept of shape, for example, circle. You see physical things that have circular shape, form the abstraction of circle. Circle as such, that precise understanding of that concept, mathematical concept of circle, doesn't exist in the world. You've never seen a pure circle. You've seen circular things. So it's a property of things. So things have properties. Properties don't exist separate from substances. They're always color of a substance. It's always texture of a substance. Those things don't exist, but we can consider them separately. And that's the process of abstraction. Good. Okay. So what is meant by universal as opposed to particular? Another way of thinking about it is what is meant by a generic as compared to a specific?
Generic would be the idea of dog, and specific would be a dog that we've seen.
That would be a universal versus particular. That's right. Universal concept of a dog. You can have the concept of a dog, generically speaking. That's a dog. Whereas you only experience particular dogs in the world, right? That dog. That's all you've ever seen are particular dogs. So the mind, this process of abstraction is forming universals, generics, whereas what you experience are the particular things. Okay, now a higher level of abstraction would be animal. That's another generic. You see generic, you see particular types of animals, and you form the generic idea of animal. You've never seen a generic animal. It doesn't exist. A generic animal doesn't exist. All we have are specific, in fact, particular, specific. So we have particular, like that is a dog, and that's a specific kind of animal. So you have this ability in the mind to consider these generics, these universals. Okay, so what are the categories of properties? We have a means of categorizing the properties. Let's see if I can do this. Hang on, try this now. They've taken away the stylus here, so I'm doing this with my finger, which is not as good. So what is the mnemonic? Do you remember?
QQ rare poet.
Yeah, QQ rare poet. That's not in the textbook yet. QQ rare poet. The 9 categories of properties, and I draw a line after the first 2. The first 2 are what kind of general kind of property?
Intrinsic.
Intrinsic, because they have to do with the thing by itself. These are properties of substances. These are things that you can say about substances. We talk about substances, especially in physics. We say things about substances all the time. And so this is a This is just a way of talking broadly about the kinds of things you can say about substances. So quantity and quality have to do with the substance by itself. These are the first two, quantity and quality. And then the last seven, can you name them? Who can do it for me? Somebody who hasn't had a turn yet. Miss Wheeler.
Relation, action, reception, place orientation, environment, time.
Good. Quantity, quality, relation, action and reception, place, orientation, environment, and time. Okay, so what is quantity? The first one. The order is very important. What is quantity? Mr. Sutton, do you remember?
Is it like the extension?
Good. Extension and having parts outside of each other. Those two aspects. Physical things have extension. All physical things have extension. It's the base property of physical things, having extension. And to have extension then, in having extension, things have parts outside of each other. They're separated from each other, outside of each other. Okay, so that's the base physical property, quantity. It's not number primarily, but number comes from quantity. What is number in relation to quantity?
Abstraction.
It's an abstraction, yeah, but it's a particular kind of abstraction.
Analogy?
Not quite. Not yet. You're thinking of measurement, I think. So number is a whole with parts. That's where number comes from. I have parts, and I can start counting these parts. These parts are similar to each other. I can start counting the fingers. Right. Okay. Quality is the other one. What is quality? A little harder to describe. It's very broad, actually. There are lots of qualities. So if quantity is how much, quality is
What kind?
yeah, what kind or how. The manner or mode of existence. So what are some qualities?
Shape.
Shape,
Color.
color,
Temperature.
temperature.
Mass.
What was that?
Mass.
Mass, good. Okay. Now notice these are things like temperature you might think immediately numbers, so don't measure yet. We're not there yet, okay? Because the measurement is not a quality. So, but temperature, meaning like it's hot or it's cold, that's a quality of a thing. Can you make a distinction between quantity and quality? Quantity is like length, area, volume, not measurements again. We're not measuring things yet. So what is, can you describe the difference between quantity and quality?
If you
Go ahead, Mr. Bigot.
isn't quantity like if you add more, then it changes.
Yeah, there's a better way. You're on the right track. Who else was going to?
If you add like two quantities together, you end up with a larger quantity.
Right. Quantities amount. Put two quantities together, you get a greater quantity. Qualities don't amount. 100 mediocre poets don't make a Shakespeare, right? Okay. So that brings us to two different kinds of quantity. Number was one. Discrete quantity. What's the other? Continuous, right? If I don't discretize, if I don't break something down into parts, then I think of it as a whole, as a continuous length. Okay. So quantity, then I can consider abstractly quantity by itself, up in the mind, focusing on the extension and the partness of things and ignoring everything else. The time, the place, the environment, the orientation, the color, the temperature, the texture. I'm ignoring everything else. I'm going to keep just the extension, and of course, because finite physical things have finite extension, I have a boundary, which is, and so shape. So I'm throwing everything else I have out. I have shape and the extension that's bordered by the shape. Okay. So that's focusing on quantity abstractly. And that's where number, arithmetic, and geometry come from, is that. So what is math?
Study of quantity.
Study of quantity. As that abstract study of just that abstraction. That's mathematics. And so it's not a surprise that we should be able to use physical mathematics in physics, because math is the study of the base property of physical things. Okay, good. So mathematics comes from the physical world. We sense the physical things and we form these abstractions. Mathematicals exist in our mind as abstractions from the physical world. Okay, so now we're getting to measure. So what is measure? What's measurement?
A relation.
Ms. Myers.
Analogy to number.
It's an analogy to number, right? And it's very easy to measure a quantity because I'll have a length, I'll have like a ruler, and then I'll have a longer thing that I want to measure in relation. I want the relation between those things. So this is the ruler, and this is the thing that I want to measure. How many of these rulers are going to amount to the length of that thing? So this would say that the length of the ruler, let's see, can I do this? How do I do this? Okay, the length of the ruler, this is not going to work. I should have used my smartboard, my Surface Pro. The length of the ruler is to the length of the table, as 1 is to 3. So what's an analogy? That's an analogy. That's an example of an analogy. What is an analogy? You use it all the time, just like abstraction, but you may never have heard an explanation about analogy, just like you may never have heard an explanation about math or abstraction. So what is an analogy? Can you give me an example by which I can form an analogy? Analogy is an analogy, by the way. That's kind of interesting, isn't it? Okay, so the example that I like to use is the one, the classic one. Fifi is healthy. That's the one that you see a lot. Fifi is healthy. That captures a certain meaning about the word healthy that everybody, I think, understands what we're talking about basically when you say Fifi is healthy. But you can also say that Fifi's diet is healthy. It doesn't mean the same thing exactly, but it's related. The meaning of her diet is healthy, the healthiness of the diet is that food promotes her health, right? So it's related back to the original meaning of health, of healthy. Fifi's hair is healthy. Again, doesn't quite mean the same thing. Fifi's blood is healthy. Take a blood sample. It's healthy blood. It doesn't mean the same thing, right? But all of these meanings are related back to one primary meaning. So analogical relations are like that. It's shades of meaning of a word. It's got variations in what it means, but it all points back to one primary meaning. And so that is an analogy. In analogies, we have a primary analogate that we point back to. So healthy is that. So what is an example of an analogy that we use in physics? That we used last term? Besides measurement. Measurement is an analogy. It's an analogy to a number. In that case, measurement of a quantity, it's very easy to relate back to a number. How about something else? Do you remember? Yes, sir.
Momentum to impetus.
Momentum is an analogy? Because we measured it, you mean?
Yeah.
Okay, good. So that's one possibility. Measuring a measurement. And so we talk about impetus, and we'll get to that here in a minute. The measurement of impetus is we call the momentum, to make the distinction between a property and its measurement. I guess what I was thinking of is, okay, Mr. Picot?
Like linear, like rotational motion.
We made an analogy from rotational motion back to linear motion. We had analogs that we formed, yeah. We also had energy, I said, is an analogy. Potential energy and other forms of energy that we're going to talk about relate back to what is the primary analogate in energy. Say again? Kinetic energy, right. Kinetic energy is our prime example of energy. We understand energy by making an analogy and relating it back to kinetic energy, which is the energy of locomotion, energy of motion. Okay. All right, so now we can also measure, we're talking about measuring quantity, we can also measure quality. But qualities don't amount, so this is obviously a different sort of thing. So we can measure qualities that vary in intensity. Some qualities vary in intensity. You can say, this is more than that. This is redder than that. This is hotter than that. This is harder than that. So we can order them. And by ordering, we can then assign number to it. And so we have a number scale. A good example of that is Mohs scale of hardness. You know, you can scratch one rock with another, right? So you can order them by number. But you can order redness, you can order temperature, you can order these things and assign numbers to them. Okay, so that's a process by which we can also form a number, but it's not quite the same. So the primary meaning of measurement here is analogical. The primary meaning of measurement is measurement of quantity. By analogy, we can measure quality, and there was one more measurement that we made. Remember what it was? We measured quality, we measured quantity, one of the other categories. Time. How do we measure time? Well, we compare one change to a basic change, which is the clock is moving. That's our base unit of change. We're going to look at one change compared to another change, and we're measuring time. So time is a measure of change, one change compared to another. Okay. On this list is not change. Change is not on this list of properties. What is change?
A process.
It's a process of what?
A potential becoming actual.
Yeah, something potential becoming actual. This is here now. It's potentially over there. Okay, now it's over there, actually. So it was there, so that change occurred. Okay, but at any given time, it had a place. Place is here, place is here. Now the place is changing. At any given time, it has one place. And the change, the motion, is not a property of the body. Not fundamentally speaking. As I slide that thing over there, that velocity, that change, is not a property of the body. It has a different place at different times, and we observe the change. We can talk about the rate of change of place, which is speed. How fast is that thing changing place? But the speed is not itself a property of the body. Okay. So, measure is not the property. We can measure properties, but the measurement of the property is not the property itself. It's an analogy to a number. It allows us to write numerical relations, equations, which are going to be useful in physics, because we're going to focus a lot on quantities, measurements of things. Okay, so all of the things that we're going to use, all the mathematicals that we're going to use in this course come from the physical world. So what is a vector? Give me a physical example of a vector. So what I mean is illustrate the concept that is captured by vector, the physical property, aspect of the physical thing that's captured by the concept of a vector.
Tree.
A tree, yeah, or an arrow. It has a length and a direction associated with it. So a vector, primarily speaking, is a length and a direction. It's not a list of three numbers, even though we learn to make calculations about vectors by forming numbers. It's not primarily speaking a list of three numbers. A vector has length and direction, or a magnitude and direction. We can extend it to talk about anything that has magnitude and direction. So what's an example of something that has length and direction? Well, an arrow, or a displacement going from here to there. I'm going to keep trying this. There we go. It's not too bad if I do it like that. From here to there, a displacement that has an ordering to it, and so it has a length and a direction associated with it. But what else? We could form other kinds of vectors that don't have length per se, but have a magnitude. So what would be an example of something that doesn't have a length per se, but has a magnitude and direction? Yeah.
Like a velocity vector.
A velocity is an example, right. Velocity is not a length, it's a rate of change of place. So a velocity is a vector, and so it's a generalization of this idea. The magnitude is now not a length per se. A force would be an example. A field, generally. So what is a field? There's the mathematical idea, so what would be a physical idea corresponding to that? Let's try to paint them both. Can you give me a physical example of a field? Gravity, okay. And so, why do we call it a field?
X at a distance.
Yeah, there's more.
The same at every point.
Yeah, it's got a vector associated with it at different points. And so the vector associated with a gravitational field will tell you what is the strength of the force acting if I put a body here, or if I put a body here, or if I put a body there. So it's in an extended region. Every point in that region has a vector associated with it. But you don't have real vectors, right, crowding in there, overlapping each other. It's not like that, right? So what we talk about is the strength of the force that would be produced on a body at this location, and then I can sample it at different places. Every one of them has a vector associated with it. That's a field. A vector field is something like that. And an example would be a forest of trees, would be a kind of physical example of what are the lengths of the trees in different places. Okay. Okay, so we also talked then about shape, and the process of measuring a position versus time produces a curve. For example, if I measure the location, the distance from here to there of a body that's moving, and I measure that distance, and I measure the time, and I actually get, of course, a series of discrete measurements, but I can connect them by a continuous line. And I say that I have now produced, by that process, a shape. So I've gone through a series of analogies. I've made measurements of place and time, and I've connected these measurements, and I've now connected motion into a shape. But this thing is static. It's not changing. Mathematicals are like that. Circle is circle, right? Parabola is a parabola. But I've gone through this process of, by taking an analogy, I can take measurements and get a shape out of it. So I can have different shapes that correspond to different kinds of motion. So, for example, just a horizontal line, what does that correspond to? What kind of motion? It's not moving, right? Or it looks a straight line that has a slope to it. Uniform linear translation, it just moves uniformly. Or a parabola. It's falling. It's free fall. It's falling down. Or sinusoidal wave like that. Simple harmonic motion, put a mass on a spring. So I'm making analogies now from a kind of motion that I observe to a shape. It's not an obvious step. It really takes some thought to realize what you're doing here. Okay, and now further, we're going to continue that even further. So for the example, I should go back here. Okay. Okay, I want to start with that one first. Let's take that one. That one clearly has a slope to it, and the slope is the rise over the run, and there are things that have greater slope, and there's a difference between positive and negative slope. And so the slope gives us a measure of the rate of change of place. So in fact, the slope is the analogy, it's the analog to the velocity. Okay, and then we can do the same thing for a case where we have a curve. But now I have to be particular about the time when I measure it, because I can connect 2 points here and draw a line through them. But how many places where it touches the curve, if I drew it better, it would cross the curve at 2 points. And the slope of that depends on what 2 points I use. And if I can bring those 2 points closer together, then the slope of that gets closer to the slope of the tangent. The tangent is the line that touches the curve, just kisses it once. Doesn't touch it twice. But in this limiting process, the slope of that line that crosses it twice approaches the slope of the tangent. And so we can talk about an instantaneous speed, an instantaneous velocity. We can compute by doing this limiting process. And so we get to derivative. The velocity is the derivative of the position versus time plot, or it's by analogy to that. Okay, so there are 4 kinds of change that we talked about. Do you remember them? Well, that's right. Okay, accidental versus, or change of property versus change of substance. Okay, but that's a little broader than what I was thinking. So One of the types of change is a change of substance, which is like the squirrel dies. You know, that's a substantial thing that happens to the squirrel, right? It's not a superficial thing for the squirrel to be conceived or to die. It comes into existence. Or you take hydrogen and oxygen together in a jar and put a match to it, it pops, and you get water. That's a substantial change. So that's called generation or corruption. Okay, a substance comes to exist or not, or goes out of existence. Okay, now let's talk about change of properties. There's three kinds of change of properties. Locomotion is a change of place, and there's two others. Go back to the categories again. Growth is a change of quantity. It gets bigger, it gets smaller. Growth or diminution. Change of quantity. Change of quality is an alteration, generally speaking. Change of color, change of temperature, change of texture. Those are alterations. Locomotion is a change of place. Locomotion is the most important change we consider in physics. Why? Why is it first?
There could be no change.
That's right. In order for me to change you, I got to come and do something to you. I got to go across the room and do something to you, right? So locomotion makes it possible for two substances to contact each other. So locomotion is really the fundamental first step in physics. And if you try to skip over it, you're losing something. And the most important thing to recognize is what causes locomotion. That's fundamentally the first thing we have to come into contact with. After we have these basic general things that we talk about, causality, property, substance, the next thing we have to confront is change of place and what causes change of place. Okay. Okay, so what is the cause of a change of place? Impetus. And what is impetus?
Property enacted in a body that causes it to move at a constant rate in a particular direction.
Right. Pretty close. You're almost precisely right. So what category is it?
Quality.
It's a quality. Yeah, it's a quality. Why is it a quality and not a quantity? Why is momentum? Impetus. Why is impetus a quality and not a quantity? First, let's back up a little bit just to make sure everybody understands the idea, and from Mr. All, who's been catching up with the reading. The impetus is the cause of locomotion in the short form. A body moves because it has impetus. That's what makes it move. How do you know it has impetus? When you see it move. So the order of cause and effect is often the reverse of the order of discovery. I see the effects and I deduce the existence of the cause. That's how I come to know that the cause is there, because I see the effects first. But the effects are follow the cause, right? The cause has to do first be there in order to cause the effect. So causality is one order and discovery is maybe the opposite order. Okay, so impetus is the cause of locomotion, and I can deduce it has impetus by watching it move. So, and it's a property. Specifically, it's a quality. It exists of the body by itself and not in relation to other things. Okay. So now, and we can measure impetus. Impetus has both direction and magnitude. In fact, we talk about how many types of impetus are there? 6. Okay, you might think 3. Why 6? 6 is correct. Why 6?
You can go forward and backwards in any direction.
Right, that's right. Forward and backwards, left and right, up and down. We're so used to this process of measuring things to think of left and right as being, well, basically just the same thing, just positive and negative, right? We talk about it that way. But I can move 2 steps left, or I can move 2 steps right, but I never move negative 2 steps. You never do, right? But we talk about negative as a means of denoting direction. And the reason we do that is because it helps us to form a simple mathematical system to describe displacement. Instead of saying that west and east are different directions, now I just talk about east, and I could move negative 2 steps east, which means I move west. And so it becomes a simpler way of capturing displacements. And corresponding to each kind of displacement is an impetus. So there are 6 different kinds of impetus, but we're going to collapse them down to 3 in terms of the mathematical description of the vector. So just like a displacement has 3 components, I can have this way, or this way, and so I reduce it to 3 components in the vector. Same thing I can do with momentum. I can reduce measurement of momentum to a measurement of 3 numbers, which are positive and negative. Okay. Okay, so what is mass?
The receptivity of a body to the action of the impetus.
That's right.
And it's a quality.
It's a quality that's related to the receptivity, right? The action of the impetus and the receptivity of the impetus. So the impetus causes locomotion, but you put the same amount of impetus into 2 bodies, same intensity of impetus into 2 bodies, and one moves faster than the other one because it has less mass. So it's in the category, we talk about it as being receptivity. More precisely, we might say resistance, which is a kind of receptivity, because we talk about more or less mass. The greater the mass, the less it moves as a consequence of having impetus. Okay, so that's mass. Later, we'll refer back to inertial mass, because we're going to talk about gravitational mass. Mass also produces a gravitational field and receives a gravitational field. And so we'll talk about those are also called mass. So what we mean primarily by mass is this first definition, which sometimes is called inertial mass, because it refers to locomotion. Okay, so, and momentum is the measure of the impetus. And we denote it with that letter P in the equations usually. Force is what? Ms. Myers?
The ability of something to change the impetus
Of another. That's right. Yeah. So it involves 2 things. It's a relational in a sense of causing the change of impetus of another one. Right. Kinetic energy. Mr. Bicot. Good, right. It's a different kind of measure of kinetic activity than momentum. Momentum has a direction, kinetic energy does not, but they're somewhat redundant. For a single body, it's somewhat redundant to talk about both the momentum and the kinetic energy, but we talk about, especially when we have a collection of bodies to form a system, then the total momentum may be 0, but the kinetic energy, the total kinetic energy will not be 0, because the kinetic energy always accumulates. There's no negative kinetic energy, so it always accumulates. So you have a measure of the kinetic activity of a body that always accumulates, whereas momentum can be counter to each other and have a net 0 momentum. But there's stuff going on inside. Okay. Okay. What is Buridan's law? I'll go ahead and write it down. That's Buridan's law. And so P is the cause of the, that says cause. This is the resistance or receptivity. And this is the effect. Okay, by writing it in this form, we make a clear relationship. We're trying to highlight the relationship between the cause and the effect. But we're going to have lots of equations which relate things which are not of this kind, don't have a causal relation captured in them, right? The number of apples and the number of oranges may be the same, but there's no necessarily causal relation between them. Okay, so not all equations capture causal relations, but we want to understand cause and effect, and so we're going to try to highlight that in appropriate places, cause and effect. And that's going to be really big in this course. Electricity and magnetism is a highly mathematical subject, and it's a real challenge for students to have a physical understanding of what they're doing in electricity and magnetism. And that's where this textbook really shines. I mean, as good as the first book is, the second book is really outstanding, because you'll really understand much better what it is that you're doing in this class than most students, because it's such a heavily mathematical subject. It's easy to get lost in the math and to just start relying only on the math and not really understand what it is that you're doing. Okay, so Okay, so, and of course, Newton's laws of motion. I'm going to skip that. Yeah, okay, so what is the work energy theorem then? We had two forms, a differential form and a kind of finite form. Yeah, Mr. McKinnon.
dW equals dk, which is the change in work equals the change in kinetic energy.
Yeah, so this is for a small displacement, the force acting over a small displacement, dr, produces this is called the work then, and that produces a change in the kinetic energy. And we can write that in finite form, and we're going to be doing this more in the finite form in this course because we're going to introduce integrals and start doing integrals finally. We've been postponing that, but not going to do that anymore. So the work is then going to be the integral of the force dot displacement. We'll talk about integrals and how to manage those. And this will then be a finite change of kinetic energy. So these, okay, this gives me a 5-minute warning here. Okay, the recording ends, which is why I have to keep being conscious of that. Okay, so the finite change of kinetic energy over a finite displacement is a result of force acting on the displacement. So, for example, here's, and we probably should have done this. Let's go through this thing for. I'm gonna throw this up in the air. Actually, let's just drop it for now. I'm going to drop this, and so I want somebody to explain what happens in terms of the principles: impetus, mass, and force. Right. Yeah. Mr. Hetherington.
Once you release it, the only force acting on it is the force of gravity,
Right.
which is received through the mass of the object, which then begins to add impetus to the object, causing uniform linear acceleration to accelerate, continually adding impetus until it lands in your hand, where the force of your hand counters the impetus in the object to bring it to rest.
Pretty good, pretty good. So the key principle is impetus, and it begins with no impetus. And as you said, there's a force acting on it. You said it acts through the mass. It's not quite right because we have mass, and it might be because you're thinking of gravitational force as well. So mass is involved in two different ways in this aspect. But the key thing here is to focus on the impetus, and there's a force acting on it that now gives it downward impetus, and as a result, it starts to move. But the force continues to act, and so it continues to increase its impetus, and as a result, it continues to move faster, so it accelerates as it falls. Okay, so that's a simple explanation of that. And you could do the same thing by tossing it up in the air. If it begins with upward impetus, then it has to lose that initial upward impetus. So it has a force acting on it in the opposite direction, and as a result, it's losing impetus, which means it's slowing down. So that means that in one case, when the ball is moving upward, gravitational force is acting contrary to it, so the displacement is up. In the other case, when it's falling, it has a displacement downward, and the force, of course, of gravity is downward. And so the dot product between those two vectors tell you whether the kinetic energy is going to increase or decrease. When it's moving upward, it's losing kinetic energy because the displacement is opposite to the force. When it's falling downward, the displacement is parallel to the force, so it increases its kinetic energy. So this is just an expression. The work energy theorem is simply an expression of Newton's laws, and then the integral form. There's nothing contained in here that isn't contained in Newton's laws. It's just a consequence of Newton's laws. And we could derive it. In fact, we did derive it from Newton's laws. That the force is and specifically that the force is the rate of change of the second law is expressed in this form. Okay. All right. So I'm going to end. We'll continue the review on Friday, but I do want to talk about one word: imperiometric. What does that mean?
Empirical is quantitatively measured.
Yeah, considering the world in terms of quantity and measure of that quantity, forming a system of symbols to handle that. which is the mathematical system. So what is the relationship of empiriometric thinking to modern science, or to science generally? No, we could say to modern science.
Modern science relies very heavily on the empiriometric, which
Yeah.
loses some aspects of reality.
Right. Modern science focuses, the core of modern science is the empiriometric. That's the core of modern science. You hear a lot of discussion about modern science is forming hypothesis and controls and doing empirical tests and that kind of stuff. Nothing about that is modern. That was done for years before modern science came into play. Modern science is based on the empiriometric. This is the core. This is the innovation that made modern science possible. And when did it happen? What was the first fully empiriometric theory?
Kepler's laws.
Not Kepler per se, because Kepler was just kind of schema, is organizing observations that Tycho had done. Newton's understanding of planetary motion by combining his second law with the universal law of gravity. Those two things together. So he had a mathematical system he could solve and demonstrate that Kepler's reduction of Tycho's observations were consistent with that. The 1 over r squared force law and the universal law of gravity and the equation of motion. Okay, that was the first example of the first fully empiriometric theory, and that's when modern science begins at that point. And what makes that possible is Descartes' invention, the development of algebra a few years before that. That did not exist before, and that was the innovation that made all of this possible that we're going to be considering in this class.